All right, so we're going to go over a variety of questions, and we're going to go relatively quickly so we can get a lot of questions in. However, you're welcome to push pause, and I strongly encourage you to push pause and work through the problems before I go through them. If I go through them, then it's a lost opportunity for you to exercise and to find the question, develop the question in your mind for yourself. If you just look at the answer, you're not going to gather what you need to gather. So please take advantage of this opportunity and work through every problem by pushing pause after you look at the question, read through the question, and then try to formulate an answer for yourself. All right, so the first question: which compound should have a higher vapor pressure at 25 degrees Celsius? Push pause now and take a shot at it. Okay, so hopefully you've had a chance to take a look at this one. We're looking for vapor pressure. Vapor pressure is when you have a container of some sort, right? And the in the container is, well, I should tell you right now, just in case you got it right and you want to move on. Okay, so the answer here is D. So if you got that right and you want to move on, you're welcome to move on now. But vapor pressure occurs when there's a container and there's another liquid inside this container that evaporates. And the more molecules you have floating around in this container, the higher the pressure is that's being placed on this outside. So a compound with high vapor pressure is a compound that has very low intermolecular forces. And intermolecular forces are based on whether or not it can hydrogen bond, whether or not there's a dipole, whether or not, and if there's not either hydrogen bonding or dipole, there's always London forces or dispersion forces, and those forces are amplified by mass. So here we have carbon dioxide and sulfur dioxide. Both of those, now sulfur dioxide you should draw because if we draw sulfur dioxide, we see that it looks like this. And that is a not a planar molecule. So even though sulfur dioxide has a larger mass than carbon dioxide, because it's not planar like carbon dioxide, the result is that carbon dioxide is the one that has the highest vapor pressure, the least intermolecular forces. All right, so going on to the second one here now. Calculate the interplanar spacing that corresponds to diffraction beams of X-rays at 20 degrees and a wavelength of 141 picometers. That's the wavelength, and we're assuming that n equals 1. All right, now you would probably have to look up the formula for this one. Go ahead and look up the formula and see what you can do. Okay, so the formulas for me are at the bottom of the page here. So I'll look up the formula. All right, which formula is it? Okay, so the formula is this one here. The n equals lambda, n lambda equals 2d, d being the interplanar spacing, sine of the angle at which the wavelengths are hitting the surface. So if we put in for n, our 1, lambda, our wavelength 20, sine of omega there, wavelength is 141, omega is our angle 20, we should get a value of 206. All right, on to the next one here. We have vapor pressure of methanol being, okay, so I want you to take a look at it and you try to do it yourself. Also, there we go. After you're done trying to do it yourself, and then you can listen to my explanation. All right? Okay, so hopefully you've done that. The vapor pressure of the methanol at 30 degrees Celsius, 160 torr. How many grams of a non-volatile substance do we have to add so that the solution's vapor pressure will be 140 torr? Okay. Well, the relationship between vapor pressure and vapor pressure of a solvent and vapor pressure of a mixture is the mole fraction. So if I have the pressure of the solution, that's going to be equal to the vapor pressure of methanol times the mole fraction of methanol. Okay? So I would like the vapor pressure of the solution to be 140. I have the vapor pressure at 160. If this was pure methanol, it would be 160. So then I can find out what I need my mole fraction of methanol to be. The mole fraction of methanol needs to be 140 divided by 160. All right, 0.875. So 0.875 should be the mole fraction of methanol. Now, how do I get 0.875? Well, I'm going to have to add some moles of the glycerol. All right. So if I have 100 grams of methanol, that's CH3OH. The molar mass of this stuff is, let's see, carbon 12, 16 plus 12, 28. This is 16 plus 12, 10, 20, 26, 27, 28, 29, 30, 31, 32. So we have 32 grams per mole for the methanol. And then that tells me that I have 32 grams of methanol for every 1 mole of methanol. So 100 divided by 32 will tell me how many moles of methanol, which is 3.125. So I have 3.125 moles of methanol. All right. And my mole fraction is found by taking moles of methanol plus moles of, what is this we're adding? Glycerol. And we need the moles of methanol on top, 3.125, right? And I don't know how many moles of glycerol I'm going to add, but that's what I have to find out. Okay, this has to equal our mole fraction, which was what? 0.875. 0.875. So 0.875 needs to be the mole fraction of the methanol. So 3.125 divided by 3.125 plus x times 0.875. So I need to go 3.125 over, or I'll multiply 3.125 by 0.875 plus x equals 3.125. So (2.73) plus 0.875x equals 3.125, and then we'll take 3.125 and subtract the 2.73, and then we'll get 0.390 divided by 0.875. So 0.446, x equals 0.446, and that's how many moles of methanol, moles of glycerol I need. And glycerol, let's see, C3H5OH3, C3, that's 36 plus a total of 8 hydrogens plus a total of 3 oxygens. So that's 92 grams per mole. So 92 times our 0.446. So 41 grams, 41 point, well, a little low, 41.1 grams. So the answer to number 4 is C. All right. Number 5, go ahead and take a shot at it. Turn off your, or push pause. Go to look for any equations that you think you might need. Try to take a shot at this one, okay? So it says, take 75 minutes for a concentration of reaction to drop 20% of its initial value in a first order reaction. What's the rate constant for the reaction in units per minute? Okay. Well, if I was dealing with a zero order reaction, now you don't have to remember this. You can look at find the equation, and the equation would be provided for you. But I'll help you remember, and in that process kind of learn more about the equations. If you already got the answer and you want to move on, the answer is supposed to be B here, and we'll make sure we can get the answer. But if I want to know the concentration of some chemical, so if A is going to be here, B, and we have some chemical reaction, and we want to know the concentration of A at some given time. So for example, if we want to know A at some time, that will be the concentration of A initial minus the rate at which it disappears times however much time we let it occur. That is the integrated rate law, but that only works for a zero order reaction. If we want to take it a first order reaction, we have to take the negative log of those, right? And the negative log in this sort of a scenario here, all right, what they're asking is that the reactant to drop to 20% of its initial value. So maybe we start with a 0 here, start with 100, so the natural log of 100 at some given time, t, our natural log, our concentration, not some given time, it says 75 minutes, right? Falls down to 20% of its original, so natural log 20 there. And then we'll have K here, which we're solving for. Now this is the first order integrated rate law, which is an equation likely to be given to you. Okay? So I can go natural log 20 here, and then I can subtract natural log of 100, and then I can divide by, I'll get rid of this negative sign by dividing by negative 75, and that leaves me with 2.15 times 10 to the minus 2. Yeah, so that's B. Okay, so strontium-90 has a half-life of 28 years. How long will it take for all the strontium-90 present on Earth to be reduced to 1/32 of its present amount? 1/32 of its present amount. So, take your time and try to figure out this one. All right, hopefully you turned it off and you took some time to mull over and try to figure it out. The answer for this one is A. If you got it right, you can move forward. If you want to go over it, we'll go over it again. So this is a half-life equation, and then when you see half-life, you also want to remember that a first-order integrated rate law is our half-life, okay? So if we know that it has a half-life of 28 years, then what that does for us is we could put in the 28 for our t here, right? Let me rewrite this for you. Natural log of concentration of reactant at some time is the natural log of the concentration initial minus kt. All right? So if we know our half-life is 28 years, so at time 28 years, then this initial concentration, we can call it 100, will go down to 50. All right, so natural log 50 minus to 100. And then we can identify our K with that much information given. And then, if after we solve for K there, so I'll solve for K really quick. Natural log of 50 minus the natural log of 100 divided by 28. Oh, and then it's a negative 28, so divided by that negative would be 0.02475. So our K equals 0.02755. Okay, so that's our K for this reaction, and now we can use this integrated first order integrated rate law again and use that K this time for the scenario that they're interested in, which is how long will it take for the strontium-90 to reduce to 1/32 its amount. Alright, so 100 divided by 32, we'll put in 100 and 3.125. Okay, so that's, if we start off with an initial concentration of 100, the natural log of what it is, how far we want it down, which is 3.125. Then our K we can use now, minus 0.02755, and then we can solve for T here and find out how much time that requires. So here we go. Natural log of 3.125 minus natural log of 100 divided by negative 0.02755. Okay, and that should be our time. We got 125.8 years. Figured out what I did wrong. I didn't copy this down right. I said 0.02755. It's 0.024755. So if I finish this one up now with that value, natural log of 3.125 minus the natural log of 100 divided by 0.024755. And I should have put in the negative sign there, but then that gives me 140 years. All right. Excellent. Next one. Okay, here's the next one we're going to go over. Take a look at this one, see if you can solve it. All right, hopefully you took a look at it. So if we have a Kc provided for us, and we have concentration of bromide ion added into solution, all right, we want to see that the Kc, which is 360 for this reaction, is equal to the concentration of the chloride ion over the concentration of the bromide ion, and that's all. So if we have an ice table to help guide us through an understanding of what's happening, our initial concentration for, and I'm just going to include the bromide ion and the chloride ion because the solids don't shift the equilibrium. And we start off with 0.1 molar of this and 0 of this. That's helpful. We know the shift is going to the right, minus x plus x. The equilibrium concentration, 0.1, and then minus x, and then this one here is x. And so this up here, concentration at equilibrium, we can call x. This down here is 0.1 minus x. And that has to be equal to 360. All right. So we can't get rid of this x here because 360 is a pretty big Kc. We'll have 360 times 1, or 0.1, which is, we'll have to distribute this through, so it's 36 minus 360x, and that will be set equal to x. We can add 360x to this side, so we have 361x set equal to 336. So then we can take 36 and, whoops, 36 and divide by 361. So we got 0.0997, which is pretty close to 0.1. So the answer there is C. All right. Next one. Okay, try to take a look at this one here. For which of the reactions is Kp equal to Kc? Take a shot at it yourself. You're going to probably have to look up a formula. All right. Okay, hopefully if you took a shot at it, push pause, look it up. The answer here is A. Okay, so now why is the answer A? Well, the formula, if you looked it up, and I'll look mine up down here at the bottom of the page. So the formula for this reaction is that you can find Kp by taking Kc and multiplying it by RT raised to the N, to the change in the moles of gas. So if there's no change in moles of gas, then Kp will equal, say, Kc, because if you raise RT to the 0, then that side just equals 1. Okay? So, looking at the first one there, the moles of gas on the right is 2. Moles of gas on the left is 2 for A here. So that's how we knew that Kp would be equal to Kc here. The second one here, we have 2 moles of gas on the left and only 1 mole of gas on the right. Third one, we have 2 moles of gas on the right, 1 mole of gas on the left. All right, very good. All right, see if you can take a look at this one and solve it. All right, hopefully you took time to push pause and try to solve it. The answer for this one is D. 13 is D. So if you got it, move on to the next one. If not, let's go over it together. Which stress will drive the following reaction to the right? Well, if we add methanol, that's adding product, so that's going to drive this reaction to the left. If we remove hydrogen gas, that's going to shift this to the left also. Decreasing the pressure, changing the pressure, how will that affect things? Well, if we decrease the pressure by, let's see, that means if we decrease the pressure, then it's going to shift toward the side which has the fewest moles of gas on it. So moles of gas on the left is 3, moles of gas on the right is 1. So if we, did I say that right? If we decrease the pressure, we go to the side with the most moles of gas. Sorry. When we increase the pressure, we go to the side with the fewer moles of gas, because increased pressure, smaller volume, you can think of it that way, then the fewer moles of gas are going to want to exist. So decreasing the pressure is going to shift this to the left because there's more moles of gas on the left. Decreasing the temperature. Well, how is temperature involved here? Well, we have delta H negative, so that means we could add in here as a product heat. All right? Because that is an exothermic reaction. The negative sign means it's an exothermic reaction. So, if we decrease the temperature, that's equivalent to removing, in this case, heat or a product. And that's going to shift the reaction to the right. And so that's why the answer is D. Okay, here's the next one. Take a second, push pause, try to solve it for yourself. All right, hopefully you push pause. I'll tell you the answer. If you got it right, you can move on. If not, please stick with me and we'll try to go over it. The answer for this one is A. All right, so how does this work? Well, we have given chemical reactions with given Kcs. Let's spread this one out a little bit so we can see it a little bit better. All right. So, and then we want to know what the reaction is for this, or the Kc is for this reaction here. Well, I can see that this is what? This is similar to these two reactions in some way. How is it similar? Well, what we've done is we've taken this second reaction, flipped it, and then added it to this top reaction. All right. Oh, and we also multiplied this bottom reaction by 2, didn't we? So let's write that out so that we can visualize it a little bit better. Okay? So we took the top the second reaction, we flipped it, CH3OH plus hydrogen gas going to CH4 and water. Okay, and then we multiplied it by 2. And then we added it to the top reaction there. which is 2 CH4s in equilibrium with C2H6 and hydrogen gas. So once we add these two together, the 2 CH4s cancel out. This cancels out. We're only one of these left. So we have 2 CH3OH combining with the hydrogen gas, and we're left with a C2H6 and 2 H2Os. All right, so that's our chemical reaction. So we took the first one and added it to a flipped, doubled second one here. So what do we do with their Ks? Well, I told you many times now that the way to remember how to treat Ks is to take simple reactions like these ones. Simpler than that. A going to be in equilibrium, and C going to D in equilibrium, and then writing the K values, which in this case would be B over A. K would equal B over A for that reaction. K here would equal D over C. All right, and then add them together and find out what the K would be. It's going to be concentration of B times concentration of D over concentration of A times concentration of C. All right, and then compare these two. And the concentration of B times D over A times C, it's these two multiplied together. All right. You can also think of it this way. If I were to add a second A to B to this one, the result would be 2 A's going to 2 B's, and this one would be A squared over B squared. So if I take this one plus this one, it's like, or if I change this to put a 2 in front, it squares a K. All right, so back to our problem then. I have to take 9.5 times 10 to the minus 13. Oh, and if I reverse it, if I reverse a reaction, so if I go B to A, then the K is going to be concentration of A over concentration of B, which is the reciprocal. So upon reversing that, this 9.5 times 10 to the minus 15 corresponds to this one down here. This one up here corresponds to the 2.8 times 10 to the minus 21, 2.8 times 10 to the minus 21, but I have to take the reciprocal because I flipped it, and then I have to square it. So I take the reciprocal of it because I flipped it, I square it because I put a 2 in front of everything, and then I'm going to multiply it by this. Okay? So I'll do that on my calculator now. 9.5 times 10 to the minus 15. 1 over 2.8 times 10 to the minus 21. This second value here I'm going to square. And then I'm going to multiply it by this value up here. So 1.2 times 10 to the 27th. Oh, did I put in the wrong number? Oh, it's not 1 times 10 to the minus 15, it's 10 to the minus 13. Okay, so then that is why I was off by 2 decimal points. Okay, very good. All right, so here's an easy one for you. Take a look at this one. Finish it up before you listen to my explanation. All right. Okay, did you get it? I'll tell you the answer now. If you haven't, push pause and look at it. The answer is E. In the equilibrium expression, which chemical concentration is raised to an exponent, the K for this reaction is going to be concentration of ClO minus, concentration of H3O plus, over what? Concentration of HClO, and then the water is not included because it is a liquid. All right. So that's it, and none of these are raised to exponents because there's no coefficients here. All right, so E is our answer. All right, next problem here. Try to take a second to identify the answer. All right, did you get it? If not, push. If you haven't got your answer yet, push pause and take a look at it. All right, if you got an answer and you're ready to move on, see if you got it right. The answer is B. If you didn't get that right, let's figure out why you didn't get that right. All right, so what governs the strength of an acid when we're looking at atoms? Well, the strength of the acid here, strength of acid when we have binary acids, is based on, and we can remember this by looking at this corner of our periodic table, HCl and HF, right, are acids, but HCl is a strong acid, whereas HF is not. If we look at HCl and H2S, for example, HCl is a strong acid, but H2S is not. So we see that strength of acids increases as you go to the right because HCl is a strong acid and H2S is not. But it increases going down on the periodic table because HCl is a strong acid and HF is not. So, what's stronger here? H2SE is going to be stronger because it's increasing as we go down. All right? So now why is that? Well, because the larger ions are easier to remove hydrogens from by water molecules. All right? So that's why the answer to number 19 is B. Okay, so let's take a look at this one here. Which one do you think the stronger acid is? This is easy. Take a moment, turn it off, push pause, answer the question. All right, the answer here is B. How do we know? Because HI is a strong acid. The end. Good. Okay, here's a good one. Take a look at this. Try to answer the question for yourself. Push pause if you need to. Okay, let's see if you got the answer. The answer is A. If you did, you can go ahead and move on. If not, let's take a look at what's going on. Okay, so the couplet, a couple of words linked together that you need to remember to answer questions about Lewis acids is the Lewis acid accepts a share of an electron pair. That's the little couplet. And so then we have to be able to draw the Lewis dot structures for these and find out which one is the Lewis acid, which one's accepting the share of an electron pair. So what we do is we draw this. I'm going to draw this. Okay, so we have these two reactants coming together some way, and the product is this one right here. So then we look and try to find out what's occurred here, and what we see is that, oh, whoops, this isn't O2 minus, or this isn't O2, this is oxygen with a 2 minus charge, like that. Okay, so we see what's happened here is that these electrons reached out and grabbed that right there to form this. And so with our couplet that we remember, which is a Lewis acid accepts the share of an electron pair, here is where the thing that's doing the accepting. The electrons always jump towards, have to reach out, right? The electrons can move. The atom itself doesn't move. So that's how we know that that's our Lewis acid. Okay, here's the next one. See if you can figure this one out. We have the pH of a 0.031 molar HClO4 solution. All right, we want to find out what the pH is, and then we want to know how much does the pH change if the concentration of H plus is doubled. All right, take a look at it. All right, if you looked at it and you got the answer right, you can move on. The answer was C. All right, if you didn't get it right, let's go over it together, see what happened. All right, first of all, HClO4 is a strong acid, so we can identify the concentration, or the pH, simply by taking the negative log of the concentration. All right, so if I take the negative log of the concentration, all right, so the pH is 1.508. And then the question is, how much does the pH change if we double the concentration? Well, that's 0.031 times 2. So now I'm going to take the negative log of that answer, right? And we're going to see what the pH is. Now it's 1.2. All right. So it changed from 1.5 to 1.2. And that is a what? An increase or a decrease? It's a decrease. By how much? And that's a decrease by about 20%. So that's how we got the answer D for number, or whoops, decrease by about 20%. That's C. That's C. Right. Okay, good job. Okay, here is our next problem. Take a look at this one. See if you can solve it. Push pause. Take your time. Try to solve it. All right, so the answer to this one is E. All right, E. So, if you didn't get it right, let's figure out what went wrong. So we're taking 8.37 grams of barium hydroxide, and we're trying to find out what the pH of that solution is. I'm going to find out what the molarity of the, what the molar mass of barium hydroxide is. What's the molar mass of barium hydroxide? So it tells me here that the molar mass is 171.31. So I have that many grams per mole. All right, 171.31 grams per mole, and I have 0.837 grams. So 0.837 grams. 1 mole is 171.3 grams, so this will tell me how many moles of the barium hydroxide I have. What I really want to know is moles of hydroxide ion, right? And this is where it kind of gets tricky, because for every mole of barium hydroxide, I have, for every mole of barium hydroxide, I have 2 moles of hydroxide ion, right? 2 moles of hydroxide ion. So, our 0.837 divided by 171.31 times 2, that gives us how many moles of hydroxide ion? 0.00977. All right. And that's that many moles of hydroxide ion. I can take the negative log of that. Whoops. Negative log of that. And that will be my POH. And so 14 minus that, 11.98. Oh, didn't quite finish this. I know I have 0.00977 moles of hydroxide ion, but that's not in 1 liter. That's dissolved into 100 milliliters. So that's in 0.1 liters. So that's going to make the concentration of 0.0977 moles per liter of hydroxide ion. Okay, let me move this over just a minute. Okay, so I take the negative log of the molarity of that, the hydroxide ion there. 0.00, not 0.00, 0.0977, right? So the negative log of that value there, and then 14 minus that, and that's our 12.98, or 99. Okay, very good. All right, the next one here. Take a shot at it. All right, if you took a shot at it and you got the answer, then move on. The answer is A. If not, stop and take a break and figure out what you didn't do correctly. All right, so we have a base. It's a weak base. It has a pKb of 8.82, and it's a pH of, well, we want to know the pH of a 0.2 molar solution of it. Okay, so we need to set up an ice table for ourselves. All right, this thing, C5H5N, acts as a base. How is it going to act like a base? Well, it's going to take a proton from water, CH5NH, going to get a positive charge, and it's going to leave behind the hydroxide ion. So if we use an ice table to figure out how that process occurs, it's a 0.2 molar solution. The K for this is what? Well, the pKb is 8.82. So I can get the Kb by taking 10 to the negative 8.82, which is 1.51 times 10 to the minus 9. All right, the change, we got a minus x here, a plus x here, a plus x here, 0.2 minus x, and x. All right, so this Kb, 1.5 times 10 to the minus 9, is going to equal the equilibrium concentrations of these, x squared over 0.2 minus x, small k, so I can just go 0.2 here. So I can solve for x here. So that's 1.5 times 10 to the minus 9 times 0.2. And then we want to take the square root of it. Square root of it. There we go. 1.74 times 10 to the minus 5. Wait. 1.74 times 10 to the minus 5 equals our x value. And what is our x value? Our x value is the concentration of hydroxide ion. So we take the negative log of that. And then we go 14 minus that because we're looking for the pH. So a pH of 9.2, about 26, what did we say, A? Yeah. All right, very good. All right, so hopefully that kept you busy for at least an hour's worth of studying. If you didn't, well, if you got to this point, you finished. If you didn't get to this point, if you skipped to the end, just to find out what's going on, you should go back and finish all those problems. Those are good problems to help you prepare for the exam. All right. We'll be studying again.